All right, well, hey, welcome to the last class of Math 104 Trigonometry. If you can believe it, we finally made it. So we have just one more topic we need to talk about. We're going to talk about these things called vectors. But my plan today is to show you vectors, talk about what they are, why we use them, and how it's related to trig. And then we'll spend the rest of our time kind of reviewing for the final exam that's coming up next Monday. But before I jump into that, are there any questions on homework or anything else we've been talking about that you would like to discuss? All right, I'm not hearing anything and I'm not seeing anything in the chat box, so I'm going to go ahead and hop up to the whiteboard and we'll start talking vectors. All right. So one more topic to talk about today. All of a sudden my screen went blank. All right. So one more topic left to talk about in trig. And this one is for all you science folks. Anyone who's going to go into engineering, physics, you're going to see a lot of these. If you go into like hydrology, stuff like that, we use this all the time as well. And so me being a science guy, these are near and dear to my heart. But we're going to talk about vectors. Now, you've probably heard that term before. And not just in terms of like physics and all that. I mean, great example is with COVID and everything. When we have diseases, we talk about things being vectors that are transmitting diseases and all that. But for us, vectors, these are things that have both magnitude. So think magnitude just means size, and a direction. So whenever we're talking about a quantity that needs direction with it as well, this is when we use a vector. So we don't always need direction, right? Like think about age. If I ask you your age, it's not like you're going to say, I'm 25 in that direction, or I'm 39 that way. No, you're 25 years old. You're 39 years old, right? Age is an example of something that is not a vector. Another thing that's not a vector is temperature. If I ask you how warm it is outside, you're not going to tell me it's 31 degrees Celsius that way, right? Or 97 Fahrenheit this direction. No, the temperature is the temperature. So there are plenty of things that are not vectors, but there are some things that are. So some examples of things that are vectors. All right, forces. Now, forces are just things that cause pushes and pulls. All right, so like when I lift this eraser, I'm applying a force because I'm making it move. But I am making it move in a specific direction. I'm applying that force upward, as opposed to applying that force downward or applying that force sideways. So how I apply that force causes different motion. So force needs to be a vector because it has to have a size, how hard am I pushing, but also in what direction. Similarly, velocity. Velocity is another example of a vector. Okay. So when we're going to talk about a velocity, it doesn't matter just how fast you're going, but also in which direction you're going. Because if I'm going to try to describe the motion of this pen, there's a difference between that, it had some speed, right? But it was falling down, as opposed to this, right? So I gave it velocity upward as opposed to velocity downward. So velocity is also a vector. Let me give you a list for non-vectors. We have a name for those. Those are called scalars. So I mentioned like temperature, age, and I'm going to put here speed. So speed is like velocity. This is where in the math science world, we do things a little bit differently than out there in the regular world. Speed and velocity are not synonymous. Speed is how fast you're going. Velocity is how fast you're going in which direction. All right, so there's a slight difference. That's what I wanted to put that there on our scalar list. But so we have force, velocity, acceleration, torque, momentum. I can go on and on and on and on and on. All right. In physics, so many of the things we use are actually vectors. All right. So when you're in that situation where direction matters, we're going to use these things called vectors. All right. So how do we represent them? How do we actually show something that's got a size and a direction, magnitude and a direction? Well, there are two ways we can do this. One is graphical. We can actually draw a picture that shows a vector. And then the other one is just symbolic, it's algebraic. And I'll show you both. And we use both when we deal with vectors. Okay, so first, how we do these graphically. All right, what they are arrows. That's it. We're just going to draw an arrow. And the length is equal to the magnitude. And it points in the correct direction. So if you wanted to represent, say, a force or a torque, velocity, momentum, any of the stuff on this list, the way that you're going to do it on a graph is with an arrow. So the arrow is always going to be pointing in the direction that this vector is going. And then we just adjust its length to show the magnitude. All right, so maybe this is a force. We're pushing something in this direction. How much force? Well, how long is that? If I had another vector that was shorter but pointing in the same direction, this would be a lower magnitude vector with a smaller magnitude. So they're really easy to draw, to represent graphically. Just go off in that direction. Now, what we do tend to do is no matter where the vector is, we represent it as an arrow that's starting at the origin. So I'm going to try to copy that one as best as I can. So it's got the same length and going in the same direction. We actually say that these two vectors are equal. So those vectors are actually the same. Now, this is one thing, especially when people first start learning about vectors, they don't like. But vectors, it doesn't matter where they are. I don't care where a vector is. All I care about is what direction it points and how long it is. So because it doesn't matter where it is, we always just bring it back to starting at the origin. And there's a reason that we do that. The reason that we do that is so that we can actually represent it algebraically a little bit easier. All right. Now, before I get to that, to the algebraic stuff, let's talk about the magnitude and direction business. So obviously what's going to matter is its length and its angle. Okay, so I'm just going to go ahead and call that guy theta. And if you think about it, how long that is it's kind of like the r from polar, or the hypotenuse of a triangle. And so you can now maybe start seeing immediately why this is talked about in trig, because it's no different than polar. It's no different than right triangle stuff. They're all related to each other. All right, now the size and the direction. Obviously, the direction is going to be given by some theta, but the magnitude of a vector, we use a different symbol for this. The symbol that we use is like a double absolute value. So I don't know if you can actually see that very well on your smaller screen, but this is two vertical lines on each side. And in between is going to be our vector. So I'm going to use the letter V as our standard generic vector. If I need another one, I'm going to call it U. So I have U and V. Now, something else you're going to see me do to show you that it is a vector is I'm going to draw a little arrow over the top. That's how I'm going to designate or inform you that this is a vector. You do see this in textbooks. It's not uncommon. But the other thing you'll see in textbooks, and like in your textbook, I think you'll see it as a bold V, but I can't do bold on the whiteboard. Bold looks exactly the same. So I'm going to draw just a little arrow to let you know that that's a vector. But this is the symbol that we're going to use for the magnitude of a vector. It does go by a different name. It's also sometimes called the norm. So the norm of a vector is its magnitude. All right, so if you ever see this symbol, the double absolute value, or you see something asking about the norm of a vector, then, well, that's the length of it. Okay, that's its magnitude, that's its size. And so graphically, it's really easy. You just measure it, right? You take a ruler, measure that length, that's your norm. All right, anyway, so we've got our magnitude and we got our direction. Kind of looks like that. Okay, so graphically, that's how we represent them. Now, algebraically, what we do is we actually break it into what we call components. Right? And to see how those work, I want to show you first how we do operations on these graphically. So let's do this. Let's say you want to add vectors. So suppose that we've got two vectors here. Let's say that this one is U, and then we'll have another one that looks like this. That's V. And what I want to do is I want to take U and V and I want to add them together. So here's what you do. We're going to do this graphically. You actually line them up head to tail. So remember we had this guy U. And since the vectors, it doesn't matter where they are, I'm going to move V so that it actually starts where U ended up. Okay, so I'm going to move it over here. And then it just needs to go in the same direction and be the same length. Okay, so I just copied it. But that doesn't matter. Remember, vectors, it only matters what direction they're pointing and how long they are. Doesn't matter where they're located, so it's the same vector. Okay, so there's my V. So then U plus V basically starts where U started and ends where V ends. So that black one is actually U plus V. So what we're doing here, you'll hear me say that we line them up head to tail. That's the phrase I'm going to use when I say we're going to add vectors together. we just take the head, the pointy part, and we move the other tail so that it's at that, and we line them up head to tail. And then you just start at the first one and end at the last one, and that's what you get when you add them together. All right, so you can maybe start seeing some of the issues with this if we're going to try to do everything graphically. If my vectors aren't actually together, I'm going to have to copy them and move them over. That leads to some potential error. I also have to be really precise in terms of my length and my direction. It can get a little complicated. You're going to see that the algebraic way is a little bit easier, but we need to know how to do this before we can get to the algebraic. Okay, so that's what we do when we add vectors. Now, something else that we can have are negative vectors. Like, what does it mean to have negative v? Well, you're going to like these. These are kind of fun. They're kind of easy. So let's just say that here is a vector v. Right? So it's got a length pointing in a certain direction. Negative v has the same length. It just points in the opposite direction. So negative v, oops, like parallel, like that better. This is negative v. So if you have a negative vector, it just points in the opposite direction. And that should totally make sense. Because think about every time you run into negatives when we deal with graphs. In rectangular, positive x is to the right. Negative x, no, that's just to the left. Positive y is up, negative y, opposite direction. When we were in polar, what happens when we have a negative r? You go the opposite direction. With angles, what's a negative angle? Well, instead of going counterclockwise, we go clockwise, right? So you should be very comfortable with negatives just meaning go the opposite way. And so the same thing happens here. If we have a negative vector, we just point in the opposite direction. Same length, just opposite direction. All right, now the reason I brought up negative vectors is because if we go to subtraction, subtraction is just adding negatives. All right, so if we're going to do, say, u minus v, we want to think about this as u plus negative v. So let's take these same two vectors and let's do u plus negative. So this was u. And this was v. What we need to do is take u and add to it negative v. All right, well, negative v is the same length as v, just points in the opposite direction. And again, I need to start at the end of u. I don't know, I think that's probably close enough for negative v. So imagine I just took this purple guy and I moved it over here, pointed at the opposite direction. So then u minus v is this right here. So subtracting vectors is done the same way. It's just we're going to add negatives. All right, so how are we doing so far? Not too bad, I hope. So this was adding and subtracting. Now, when we get to multiplying, this is where it gets weird. Because it turns out that there are 3 kinds of multiplication with vectors. Don't worry, we're not going to go there. You will see that later. When you get into calculus, you'll learn about the different types of multiplication and what they do. All right, but we're going to look at one of them, and we're going to look at what's called scalar multiplication. So this is where we're going to take a scalar times a vector. So what you're going to see is something like k times v. So this is where I'm going to be very careful. Make sure you know what's a vector and what's not a vector, because there's a different things happen if we have a vector times a vector. Okay, so when we take a vector and we multiply it by a scalar, what happens graphically is that this changes the length. It changes the norm of the vector. It changes its magnitude. And it changes it by a factor of k. So if we had, say, 2 times v, your vector is twice as long. 5 times v, it's 5 times as long. A half times v, it's half as long. All right, so it changes the length. It makes it longer if k is greater than 1. So I'm going to put here it lengthens if k is greater than 1. And it shortens if k is between 0 and 1. So this is how you can actually make a vector and change its length. Just multiply by a number. All right, now you notice that I didn't allow this to be negatives. If we multiply by a negative, it does 2 things. It changes the direction, what the negative does, and then it can also change its length, again, depending upon whether that number is, greater than 1 or less than. All right, so scalar multiplication. All right, now this graphical stuff, I don't want to concentrate too much on it. I want to use it though to help us get to the algebraic way of doing this, because it's way easier to do these operations algebraically than graphically. All right, so let's go back and look at a vector that's just kind of in that standard position, that's coming out of the origin, pointing in some direction. Okay, so here's our vector v. Now, what we're going to do is we're going to break it into what we call components. And the components of this vector are going to be vectors that point horizontally and vertically, that when added, give me my vector v. So notice how these two are lined up head to tail. So when I add those 2 things, I actually get my vector v. So this horizontal one, this is called the x component. And the vertical one, this is the y component. So every vector in the plane we can actually represent with as the sum of the 2 components. You take the x component, you add the y component, and it gives you the vector itself. If we were in 3 dimensions, we allowed a 3rd dimension. We just do 1 more component and go into a 3rd direction. We call it the z direction. But we'll just stay in the plane, so we only have the x and y components. All right, so we need to figure out how do we get these guys. Well, we also define some vectors that are length 1 in each of those directions. Okay, so think about the vector that points length 1 in the x direction. I just moved it off the origin so we could see it better. Okay, so this is what we call a unit vector. Just like with unit circle, remember unit circle meant radius 1. The unit vector means that it's length 1. Okay, So it's a unit vector. And this specific unit vector, we call this one I. Okay. Not the same as the imaginary number I. This is the vector I. Don't blame me. I'm not the one who named all these. All right. But that's I. All right, well, we also define the unit vector that's pointing upward. And this unit vector is named J. Okay, at least that makes sense, right? If we started with one of them being I, the next one is J. Guess what? If we go to a third dimension, the unit vector that points in the third direction, it's K. Okay, so these guys are I and J. Now, there's a reason that we need to describe these guys I and J, because the components, the X and Y components, are going to be multiples of I and J. Remember what happens when we multiply a vector by a scalar is it changes its length. So if this was length 1, I actually have to multiply it by something to make it long enough to be my X component. And the same thing, if this is length 1, I have to multiply it by something to get my Y component. And so here's how we represent vectors in an algebraic way. We're going to write them as A times I, times the vector I, plus B times the vector J. And all those A and B are the lengths of these two sides. A is the horizontal length, and B is the vertical length. So this is called the component form of the vector. And this is what we're going to use to do algebra on them. This is how we're going to add, subtract, scalar multiply much faster if we've got it written in this form. Now, because mathematicians are lazy, and because I'm one of the laziest of them all, I'm not going to write it like this. I even have a little bit more shorthand. I'm going to write it as V equals A and B. It looks like an ordered pair, but instead of parentheses, I'm putting the triangular parentheses, so greater than, less than symbol. And this is going to be the notation that I'm going to use. And you're going to go, okay, this means we're doing vectors, because it kind of looks like the arrow of the vector. And these are just the two components. This is telling me where the vector is. Okay, so that's a shorthand I'm going to use. I think the book primarily uses the AI plus BJ, but these are pretty well intermixed depending upon your class and your teacher. A lot of people bounce back and forth. So get familiar with both of them. All right, so here's how this plays out. Like if I were to give you one in this form, in the component form, here's how easy it would be to draw it, right? So for example, let's say I said we've got the vector 2, -1. Here's all you got to do to draw it. So we got our axes. Go find the point 2 - 1. So here is the point 2, -1. The vector 2 - 1 goes from the origin to that point. Easy. Oh, good Lord, it's easy. If you can plot the point, you can plot the vector. Just go out from the origin to that point, and there's your vector. All right. So I love this form. I love this form because I don't have to draw anything. If I need to draw it, it's easy enough to do so. But I'm going to be able to now do all the computations with vectors without even drawing one picture, which for me is a big deal. It's pretty useful. All right, so let's relate these just a little bit more to each other, and then I'm going to show you how you do the operations. Specifically, I want to talk about how you can find the magnitude and the direction of a vector if you're in this form. Well, this is going to be the same thing as finding r and theta in polar. It's the same as finding the hypotenuse and the angles in a triangle. So think about this. If I want to know the length of the black vector, right, v, and I know the lengths of these two, which are a and b, I just have to use the Pythagorean theorem. So the magnitude of v, that's going to be the square root of a squared plus b squared. Again, how many times have you seen this in this class? Right? Tons and tons and tons and tons and tons. All right, well, anyway, there's the magnitude of this guy. And then if you want to know the direction, well, it's the same as always. The tangent of theta is b over a. So if you want to know what direction you're going, you can just take the b and the a, divide them. Okay, so there's the link. It's the same as with polar as with everything else. No difference. All right, well, let's get to the algebra on this. Let's get to the, all right, Bruce, show us how fast this can actually be done. You're gonna like this, I promise. So, in component form, first, to add, all you do is add like components. And to show you what I mean, let me give you an example over here. Let's say we've got u is 2 minus 1, so we'll use this guy right here. And then let's say v is 5, 3. So here you go. Here's u plus v. You literally just add the x components. So I have the first coordinates. 2 plus 5 is 7. Minus 1 plus 3 is 2. So that's the corresponding vector that we get when we add those two together. If you were to draw them, if you were to put them on the coordinate plane and draw them really well, put u and then line up v head to tail, connect the ends, you're going to get the resulting vector 7, 2. Way faster. And you don't have to rely on your drawing skill, which if it was me, I'd be screwed before I even start. All right, so that's what we do to add.
Hey, Bruce.
Yeah.
I just had a quick question. My Zoom restarted and froze. So everything you wrote on the left-hand side below, I didn't hear you explaining that.
Okay. Well, just the real quick, you need more detail, you can watch this later. Yeah. But so I lost you where? Here?
Yes.
Yeah, okay. So what we're doing is we're writing it as a sum of the two vectors, the horizontal vector plus the vertical pieces. That's what these are, AI and BJ. Because we're lengthening the horizontal unit vector and we're lengthening the vertical. And then there's a real lazy way of writing it. It's just without the I and J, you write the little pointy parentheses. So that's what I was doing here. When I wrote, say, 7, 2, this is the same as 7i plus 2j. That takes way too much writing. So I'm just going to write it as that kind of ordered pair. And then this was just showing how the angles can be found and how the magnitude of the vector can be found from A and B. But this is exactly the same as polar. It's exactly the same as with a right triangle because there's a right triangle. Okay, so there was your real quick what all that was. I think you'll pick it up as we're going. All right, so if to add, you add like components, guess what you do to subtract? we subtract the like components. So let's do u minus v. So if u plus v was 7, 2, u minus v, well, 2 minus 5 is -3. -1 minus 3 is -4. So that's the resulting vector when we subtract v from u. Much better than having to draw, turn it around, line it up, head to tail. Right? Nope, this is done. We got it. Okay, so for some practice real quick, what's the magnitude of this vector? How long is it? So let's find the magnitude of u minus v. Well, that's just the Pythagorean theorem. So that's going to be the square root of -3 squared plus -4 squared, which is 5. So the vector that we got when we subtracted u minus v has length 5. What direction does it point? Well, I could do an inverse tangent and then, do my thing and I can find it. But we can find magnitudes actually also very easily when we're in this form. All right, so then lastly, how about scalar multiplying? So this was the take a vector and multiply it by some number. The way that we do this is you just multiply each component by the scalar. So in essence, you distribute it through. So let me show you what I mean here. Let's say that we've got 4 times u, or again, u is 2 minus 1. So what we're going to do is we're going to multiply both of those components by 4. So we'll take 2 times 4 is 8, minus 1 times 4 is -4. Done. And again, you don't have to worry about, did I actually extend it the right length, whatever. No, we got it. All right, so now that we see how that's done, I can actually show you why multiplying by a scalar changes the length. So let's just do a generic k times ab. So this is going to be ka comma kb. And let's find the magnitude of this. So let's just call this v. The magnitude of v then is going to be the square root of ka squared plus kb squared. If I square through, that's k squared a squared plus k squared b squared. I can factor out the k squared. And now the square root of k squared is just k. And so notice that what we have here is the length of the original vector and now it's multiplied by k. So scalar multiply does exactly what it should, which is change the length by a factor of k. All right, so I'm a huge fan of being in component form. I do it as much as humanly possible because it makes it a lot easier to do the operations, add, subtract, multiply. It turns out the other multiplications also easier if you're in the component form. And some good news for you. I know I just said that there are 3 multiplications and you're probably not looking forward to that when you get to calculus. But just to give you some good news, turns out there's no such thing as division. You don't have to worry about vector division. So we gained 2 more multiplications, but we lost a division. Pretty much. All right, so obviously getting to component form is a big deal. And if you want to find the components, you're actually going to have to do the same thing as converting from polar to rectangular. So suppose I told you, for example, that V has magnitude 10 and points in the direction of 5 pi over 4. So I just told you everything that you need to define a vector. I told you how long it is, and I told you what direction it is, right? What direction it's going. But let's find the components. Let's actually find the components so that we can then maybe, if we wanted to, add it to something else or get its length bigger or whatever. So let's find the components. Now, if you think about it, think about that picture that I drew with the vector and I showed you the components. Those are just the x and the y that are coming from a magnitude and a direction. So this is the same as converting r and theta. So remember doing r and theta to xy? Well, that's exactly what we're going to do here. So the x component is going to be r cosine of theta. In this case, r is the magnitude, which is 10. And of course, we're in the direction of 5 pi over 4. The cosine of 5 pi over 4 is minus root 2 over 2. So we get minus 5 root 2. Similarly, y is equal to r sine of theta. Same r, same theta. So now we need the sine of 5 pi over r. Well, that's also minus root 2 over 2. So we get minus 5 root 2. So this vector v then, in component form, is going to be minus 5 root 2 comma minus 5 root 2. So if you were to do the Pythagorean theorem on there, you'd see that its length is 10. And it's definitely pointing in the direction of 5 pi over 4. All right, so it's good to be able to bounce back and forth between the forms, depending upon what you're doing. And I will just tell you from my experience in the sciences and as a physics teacher, you will see a lot of vectors. You will get very comfortable with them, and you'll get very good at this conversion, the r cosine theta and r sine theta stuff. So I know it's all relatively new to you, and you guys are still probably a little uncertain, but it'll come. I promise it'll come. All right, so I just want to show you one more thing that's kind of useful to do. And that is finding a unit vector in the direction of a given vector. All right, so we're going to find the components of a unit vector in the direction of v. Okay, so v is going to be pointing just in whatever direction. I want to show you how you can find a unit vector. So let's go with the generic v equals a comma b. So pointing off in some direction wherever a and b are, but its length is not necessarily 1. And remember, that's what this means. Unit vector means that we need this to be length 1. All right, well, that means we're going to need to change the length of this vector. If it's not length 1, we're going to have to either make it longer so that it is length 1, or we're going to have to shrink it down so it's length 1. But either way, we're going to change its length, which means we need to multiply by a scalar. All right, well, the way we're going to do that is we're going to multiply by 1 over the magnitude of v. We're going to take its length, and we're going to multiply by 1 over that length. In essence, we're dividing by the length. Right? If it's length 10, I want to divide by 10. If it's length 20, I want to divide by 20. If it's length 1/2, well, if I divide by 1/2, I'm multiplying by 2. So it turns out to make that unit vector, all you got to do is divide by its magnitude. So let's take this example over here, right, where we had v was minus 5 root 2 comma minus 5 root 2. That was the one that we just found right here. If we want to get the unit vector, we need to multiply this by 1 over the magnitude. Well, we don't actually have to calculate anything because we were told the magnitude, right? Where we had a magnitude was 10. So this is going to be 1/10 times minus 5 root 2 comma minus 5 root 2. So that means we're going to take each of those components and multiply by the minus 1/10, or by the 1/10, I mean. And so the 5 and the 10 reduce, we get minus root 2 over 2 comma minus root 2 over 2. So there's a unit vector that points in the direction of v. It's not that hard to do. It's going to be a little bit more challenging when we don't already know its magnitude, and I'll show you an example of that in a minute. But let me just give you a justification for this, like why you would want this. So imagine I'm just told, okay, I've got a vector that's in that direction. If I can make it length 1, it's going to be a lot easier to manipulate it. But later, if you say, okay, hey, I want something of length 308, oh, I'll just multiply that by 308. So it's always really nice just to have a unit vector, especially when you're dealing with forces that are not in line with each other. So you've got some sort of weird tug of war going on with forces that you'll see in physics. All right, so if you're told the magnitude, yeah, just divide by that magnitude. If you're not told the magnitude, find it. Find it, and then do it. So here's another one. Let's say that v is 3 minus 4. Let's find the unit vector. So again, let's find a unit vector in the same direction. So first things first, we have to find the magnitude. So that's Pythagorean theorem. So square root of 3 squared plus negative 4 squared. Well, that's the square root of 9 plus 16, which is 5. So our unit vector then is going to be 1/5 times 3 minus 4. Which is 3/5 comma minus 4/5. So that vector has length 1, I promise. You can try it out for yourself. But that's got length 1, and it's pointing in the same direction because it's just a scalar multiple. All right, so that's how you can find a unit vector. But I want to draw your attention to something. I'm curious. I don't know if anybody saw this or thought this. When I first got this guy, this unit vector, for the one that we knew was length 10, pointing in whatever direction. When I got these components, did anybody's like ears perk up? Or when you're writing them, did you kind of go, wait a minute, those things look familiar? Because you've seen those numbers before, right? Root 2 over 2, or in this case, minus root 2 over 2. Where have you seen those?
Are they the lengths of the 45, 45, 90 triangle?
Okay, yeah, these are specifically from that 45, 45, 90. Think about this as an ordered pair. That point is on the unit circle, where in this case, I think it was 5 pi over 4 was the angle. That was the point on the unit circle where we intersect. So these were the cosine and the sine of that angle. Well, it turns out that when you go to a unit circle or a unit vector, those things are always cosine theta, sine theta. So if you know the direction that your angle is pointing, if all you want is the unit vector, it's just the cosine and sine of those angles. And now we're back, right? We just been, I don't know if you realize this, but we've been doing the same damn thing all the time. We call it different things, right? Now we're talking about a unit vector. We're finding the magnitude. Okay, well, in polar, it was, we're finding the modulus. We're finding the argument, right? And in the unit circle, unit vector, we're finding the coordinates of the point on the circle. It's all the same damn thing. It's all the same. And it all comes from right triangles, right? Like when I just asked here a minute ago about the, where did you see those before? And I was like, oh, the 45, 45, 90 triangle. Yeah, it all comes back to right triangle, which is why all of this is part of trig. So I know that, like, if you just made a list of these topics, you would go, where the hell is the triangle stuff? We're studying trigonometry. The only time we really did it was in those couple sections when we had law of sines and law of cosines. But that's when I would argue, no, we've been doing triangles always. They're just hidden. They're just hidden. And this is one of the reasons that I love trig, is that we have such a variety of topics that really all get simplified down to right triangle or the unit circle. Anyway, so there you go. One more example of where we use these. So vectors, get used to them, especially if you're going to go through that physics sequence. You will do a lot with vectors, because just about everything in physics is vectors. All right, so there you go. Math 104. We're done. So I'm going to hop back to my computer. Just it'll be a little bit easier for me to talk a little bit about the review for the final and all that. But we got a little bit of time, so let's talk about that final. But just give me 1 second and I'll be back down. All right, so that was a pretty crazy couple of months, huh? We've seen a lot. Hopefully you've learned a lot, and hopefully you're going to be served pretty well when you go forward into calculus and physics and the other sciences and stuff where you're going to use this trig. But we still have one more thing we have to do for our class, and that is we've got our final exam, right? So our final exam is on Monday. So we are lucky. We get it out of the way, right? The good old tearing off the Band-Aid or whatever. So that's really good news. Anyway, so it is on Monday. In terms of the timing of it, let me just pull up my syllabus here real quick so I don't tell you the wrong thing. Yeah, it might help if I can find it. Oh, there it is. Okay, so the final, where is it? Where is it? Oh, there it is. Okay, so we have slightly different final exam schedule because final exam week is a little bit weird. But for us, the final starts at 10 o'clock instead of 11. All right, so it's an hour earlier than we're used to. I am going to send out a Canvas message just to remind you guys all about that. All right, but it's actually going to be scheduled for 10 o'clock, and it should say that in the Canvas shell as well. I believe that I have that in there properly. At least I hope I do. So it's going to be starting at 10, and then it needs to be uploaded through Canvas by 1. Okay, I'm giving you all kinds of time. All kinds of time. I'm going to have zero sympathy if you don't get it uploaded by 1 o'clock. All right. I mean, even if you give yourself 2.5 hours for the test, which it should not take, that still leaves you half an hour to get this thing uploaded and figured out. Right. That's more than reasonable. Okay. If you're having problems, email me. Right. If it's like 12:30 and you're getting, oh, it keeps saying it won't upload, email me, let me know. But I'm going to be very unsympathetic when I get that email at 1:05. Oh, I've been trying to upload for 5 minutes and it won't work. Yeah, no, that's on you. All right. So get it uploaded by 1 o'clock. Now, in terms of what it's going to look like, it's going to be very similar format to the other exams. There shouldn't be anything on there that really throws you for a loop. It's going to be probably a little bit longer than the other exams just because there's a little bit more information, and it is going to be cumulative, meaning there's going to be stuff on it from all the way back in April to today. All right, but you can use your other exams as good guides because if you think about it, like think about this most recent exam, there were questions on solve triangles. Well, I'm going to put a solve a triangle question on the final. It had questions about solving trig equations. There's going to be a solve trig equations on the final. There are going to be identities on the final. They're like all the things that we've done along the way. The big kind of important things are going to show up again. So let me just kind of remind you where we've been and the kinds of stuff we talked about in terms of what might actually be there. So the first chapter, when we were back in chapter 7, this was really just sort of setting the table. It was giving us an idea of, what trigonometry is, and we were introduced to the functions themselves. So the big things to get from the first chapter, for sure, are just how we deal with angles, radians or degrees, how you can go from one to the other, right? And just that all angles are measures of rotation. Okay, so that was kind of where we started, and that's very important. And then all the different trig functions. We define them both in terms of the right triangle, so SOHCAHTOA kind of stuff. And we also define them in terms of the unit circle, right? X coordinate for cosine, Y coordinate for sine, and so on and so forth. So the big ideas from 7 are how we deal with angles and how the trig functions are defined. But I'd be willing to bet that for most of you, you don't really think much now about the trig functions as how they're defined. You just do them. You just use them because we've been using them for months. So that part probably isn't going to require a huge amount of going back and reviewing. All right, so that was the first chapter. Then the second chapter we really started looking at the properties of the trig functions. So we looked at graphing them. It'd probably be a good idea to go back and look specifically at sine and cosine and how to do the whole like amplitude and period and phase shift stuff. Because you know I'm going to give you one of those on the final. And then we also talked about the inverse trig functions. And we defined those as well. That's another one that I think probably by now you're starting to get pretty comfortable with. But remember that the inverse trig functions only bring you one angle in one spot. And that may not be the one that you need, right? So remember how to get from whatever your calculator tells you as an angle to the one that you need for your specific situation. All right, so the first couple of chapters, just here are the players of the game. Then we started using them. So the next chapter was the identities. For the final, make sure you make use of the identity sheets, right? You've got the one that's on Canvas that you can, download. If you want to use another one, that's fine. I expect that you're going to use identity sheets, but do not use some other technology to prove your identity for you. Okay, you guys are aware I know about this. In fact, I think we had a discussion about this after maybe exam 1, maybe exam 2, because a lot of you, I could tell, were using other resources. And I kind of let it slide, right? Because it's a learning experience, all that. But I'm not going to let it slide on the final. I'll know whether you're doing it or whether you're using some other resource. All right. If you end up using other resources, I'm 0 for the final, period. No discussion, no nothing. All right. And like I said, I can tell. It's not one of those things where you can go, oh, but I know that this is the steps. No, I know how students think. I've been doing trig. I've been teaching trig for over 2 decades. I know. I'll know. All right. So don't do it. It's not worth it. Show me what you know. And if you don't know it, you don't know it. It's not the end of the world, right? Better to get like 4 points out of 10 on that one question than 0 on the final. Okay, so don't do it. Anyway, use the identity sheets, practice them. Practice them. The best way you get good at identities is by just doing a bunch of them. You start seeing the tricks. And I definitely shared some with you. So remember that when in doubt, turn things into sine and cosine. That often is the key, right? So turn things into sine and cosine. Think about the algebra stuff that you can do. Adding fractions, factoring, right? That kind of stuff. And just start recognizing identities, and don't forget the other direction, right? You're really used to looking at things and reading them from left to right. Well, sometimes the identities are better used going from right to left. Okay, so don't forget about that. Don't forget about going the other direction. I'm not going to ask you to like prove any of the identities that we built, but you're going to need to be able to use them. So we did a lot of algebra with identities and solving equations. And that was chapter 9. So that was like all the algebra stuff. That was our 3rd chapter. And then this most recent chapter has just been applications, right? So law of sines, law of cosines, area stuff for solving triangles, polar coordinates, complex numbers, parametric equations, and now vectors. But they're all the same thing. They are all literally the same thing, just being used in a slightly different way. So if you get really comfortable with the conversion, I would suggest hitting up the polar section. Concentrate most on that, because if you're really comfortable with polar, then complex numbers and vectors are easy, super easy, because you just use the same polar conversions when you do them. All right, so in terms of things that are going to be on the test, obviously I haven't written it, so I don't know exactly, but I can tell you for sure things that I have asked in the past that I'm going to ask you. There's going to be something about angle conversion. You should definitely need to know how to do that.
There will possibly maybe be some application involving rotation. There will definitely be getting values of sine, cosine, tangent, and all that from triangles or the unit circle. There will be a graph with amplitude, period, phase shift stuff for sine and cosine, whether it's I give you a graph and have you tell me those things, or I have you build a graph from it or whatever. I don't know, but there's definitely going to be something along those lines. I'm definitely going to ask you about the inverse trig. Most likely it's going to be one of those where we composed the inverse trig with the other trig, right? The old sine of cosine inverse of 1/2 or something like that. So definitely know how to do that. There will be a couple of prove these identities. Make sure you just work one side, right? Pick one side, start on that side, and work it until it looks like the other side. Do not move things from one side to the other, because there you're assuming that it's true. And proving something is true by assuming it's true isn't a proof. That's really bad form. But anyway, so there will be a couple of those. There will be some solve the equations. And when I say some, I just mean like probably 2. Obviously, I'm not going to go in as much detail as I did on other exams. Like you think about this exam you just took, there were like 3 solve equations. I'm not going to put that many, because otherwise this final exam is going to be horrendously long. Same thing with identities. You go back and look at the identity test, there were probably like 4 or 5 confirm identities. No, I'm not going to do that. So, but there would definitely be solve equations. There's going to be solve triangle question, probably multiple. So make sure you know how to use law of sines and law of cosines. Remember my tips for when you're finding angles. If you're using the law of sines, go for smaller angles. If you're using law of cosines, go for bigger angles if you have the choice, because then you're not going to run into the or issues. So know how to do those. And then in terms of the other applications, yeah, I'll probably have you do some sort of polar conversion. I'll definitely have you do some sort of complex number something. Parametrics and vectors weren't on the other exams, but I will definitely ask you about those. So with parametric equations, the big things are being able to draw their graphs, supply the orientation and all that. And then also to be able to eliminate the parameter, get rid of the t. And then with vectors, I'll probably have you just do some real quick, here are some vectors, add them, find the magnitude, stuff like that. So that's what the exam is going to look like. Nothing should catch you by surprise at all. All right. And that's never what I try to do on final exams anyway. I'm not trying to trick you. I just want to see what you've learned, what you've picked up. Okay. Anyway, so similar structure, just a little bit longer. Anyway, so we have just a couple more minutes left. So I'm just curious if any of you guys have any questions or any last minute things you want to discuss. I'm just going to remind you also, there's one more homework set stuff due, I think it's Monday night at midnight. So don't forget to do those as well. Probably a good idea to work on them before the final exam, so that you can practice those things, so that when you see questions like those on the final exam, you're ready to go. All right. All right, well, it sounds like we're pretty good. So I just want to congratulate you on making it through Trig. I'm looking forward to actually meeting you guys in calculus. If you're going to stick around at our college Math 105, I will be teaching that in the fall. So that should be on campus, barring anything weird happening this summer. Let's cross our fingers. So I'm looking forward to actually meeting you guys. If you haven't signed up yet, do it. Sign up before you leave for the summer. Otherwise, stuff will come up, you'll kind of forget, and you don't want to be scrambling at the start of the school year. So if your plan is to still be on campus, definitely sign up for Math 105, get into that calc sequence so we can get you going. All right. So other than that, it's been real. It's been fun. It's been real fun. That's your last dad joke, I promise. Anyway, so have a great summer, and I will see hopefully most of you in the fall. All right.